Hello, everyone. I'm happy to have Elizabeth Dresselhaus present her and her collaborators' recent work about the integer quantum Hall transition. I think it's a very interesting topic, and I'm looking forward to hear the story. If you have any questions during the presentation, do not hesitate to ask. And also afterwards, there will be time for more discussion.
Okay, thank you, Anton, for the introduction, and thank you, everybody, for coming. It's great to see a lot of familiar and new faces today. So today, I'm going to try and tell this story about rethinking the integer quantum Hall transition. So this will be part about two recent papers and also trying to integrate the new findings with the old findings and tell a bit of the history. So I'd like to start off by, sorry, there's a little lag. There we go. So I'd like to start off by thanking my collaborators. First of all, thank you to Bjorn Sbierski, a postdoc at UC Berkeley, who has been really helpful in learning how to do numerical calculations and always has great ideas for what to do next. And thank you to Ilya Gruzberg, a professor at Ohio State University, who has been very helpful with the analytical side and making contact with other theories and thinking about what to do with our results. And thank you to Joel Moore at Berkeley, my advisor. So I want to lay the stage for what we're talking about today with a simple picture of a 2D electron gas. So we'll be talking about the X and the Y direction, and then perpendicular to the plane of the electrons, applying a strong magnetic field. And we know from Edwin Hall in classical physics that as soon as you apply this perpendicular magnetic field, you induce a Hall voltage in the direction perpendicular to the current. This is known as the Hall effect. So when we put this classical understanding in the context of quantum mechanics, we get an interesting picture where if we solve the quantum mechanical problem, our electronic states quantize into Landau levels. So on the right, I've drawn a density of states diagram. And normally in physics classes, you'll learn that these states are just spikes with certain allowed energies. But what happens in reality is that these spikes are broadened by disorder in the sample, so certain impurities, and we have more broad peaks here. So if we take a measurement of a 2D electron gas in a magnetic field, we got some surprises. So Klaus von Klitzing originally did this measurement on the left. And for small magnetic fields, we saw the classical expectation between the Hall voltage and the applied magnetic field, so a linear relation. But as the magnetic field got higher and higher, we started to see the effect of these Landau levels that I mentioned on the previous slide. And we see that these conductances end up being quantized, which you can see by this staircase in these plateaus. So an interesting question that we can ask is what happens between two quantized values of this Hall conductance? So if we zoom in on this transition here, we can see that between the third and the fourth plateau, for example, we have a couple of things to notice. So the first I want to draw attention to is this spike. And the other quantity that's plotted here is the longitudinal resistivity. So this is talking about what happens in the bulk of the sample. So it makes sense that between two quantized values, something would have to happen in the bulk. And we'll be talking a little bit more about that today, exactly what that is and how its role is. And then we also notice that we can measure the temperature scaling. So this is a great plot from Wenli Li and collaborators from 2009. And that's the latest, one of the latest in a series of measurements that varies the temperature upward. And we see that as we vary the temperature upward and repeat this measurement on samples, this critical point in the middle of the transition or so remains fixed. And as we lower the temperature down to 13 millikelvin, it diverges. And we can plot this as follows, as just plotting the derivative of the resistance here. There's my laser pointer. And we see that for 3 different measurements, this all collapses onto the same curve. And this has a slope given by this number, the minus 0.42. So this is a very interesting observation because we see that something doesn't change between measurements. So you might have noticed on the last slide that the critical field at which this transition happened was different for different materials. But we can posit that different measurements follow the same universal scaling law, which is that this exponent with the temperature will be the same no matter what microscopic details of your sample. And the caveats to this, the universality law, is that the universality class is defined by the dimensionality of the system, today always 2 dimensions, as well as the symmetries. So today I'll often be talking about systems with different microscopic details that we expect to have the same universal scaling law. So if we look at this universal scaling law a little bit more carefully, we see that this number breaks into 2 more fundamental exponents. So Z is called the dynamical critical exponent, and this is describing the role of electron-electron interactions in the transition. And then nu is describing the localization length critical exponent. And you can think of that qualitatively as a measure of how fast the phase transition spreads through the spatial extent of a system. And for the integer quantum Hall transition, neither of these 2 exponents is particularly a resolved problem. So I'm going to solely focus on localization length today. So this will be what we call a non-interacting theory. And the caveat to focusing on one aspect is that it's necessary to understand both to make contact with experiment. So at this point, I will be talking purely about theory. So before we spend a long time learning about localization length critical exponents and calculating them, I wanted to give a little bit of an intuitive picture for what this is. So imagine on the left that we have an energy landscape of one single disordered Landau level. And we have mountains and we have valleys, and those are just showing us what the disorder is. And we can fill that landscape with electrons, 1 by 1. And because the magnetic field and the Landau levels are proportional, we saw earlier, we can also effectively do this transition and model this transition by raising the number of electrons or the Fermi energy of our system. So we add electrons, which are these puddles here, to the landscape. And we take a cut here on the right of a topographic landscape. So these blue regions are the filled puddles. And as we raise the energy and fill this system with more and more electrons, these puddles get bigger and bigger. And we can estimate or deduce from this picture that the average size of these puddles is the localization length. And as we keep filling this and filling it further, eventually the disordered landscape will flood. So this can be seen as the localization length diverging. So it becomes the size of the sample, or if we're theorists, we say it goes to infinity because all of our samples are infinitely large. And the localization length describes exactly how fast this occurs as we approach critical energy, where we have this flood. So in order to do calculations, we need to introduce several effective models. So here I will take a pause for any clarifications, and also catch my breath. So I'll take a few seconds.
I would have a question regarding universality. So is it obvious that this C exponent is universal if you argue that it's from interactions?
You're talking about Z, not nu, correct?
Yeah.
That is a good question. And I think I am not an expert in that field. And there might be experts here who could answer, but I at this point don't know how the non-interacting or how the interacting exponent relates to the non-interacting universality class.
So I can try to say a few words here. So maybe the key idea here is to say that let's just focus on non-interacting story. And then if we understand it well, we can ask ourselves whether adding interactions at that critical point is a relevant perturbation or irrelevant perturbation. Right, so this problem has been studied, and the conclusion is that it's certainly irrelevant for short-range interactions, okay? And long-range interactions, such as Coulomb, are relevant. So when the interactions are relevant, you cannot say pretty much anything about what happens, okay? When interactions are irrelevant, then they certainly do not affect the localization length exponent, or shouldn't, but they introduce dephasing in the system, right? So the particles that move in there start to dephase, lose their coherence. And then you can ask, the initial question to ask is, what's the associated length scale with the energy relaxation, the momentum relaxation, the phase relaxation? And it turns out that all these things diverge as temperature goes to zero, but with different exponents. So there's not even a single Z exponent in this sense. There are several of them, depending on what process you're looking at, okay? So that's sort of a short answer to what you might ask. So it's not a good question whether it's universal or not. I mean, there are several of them, and they depend on the detail of scattering, for example, on inelastic processes and stuff like that.
Okay, thanks, Celia, for the clarification. So, yeah, as I said before, I will focus purely on the non-interacting picture, but the interacting picture is also filled with a lot of very interesting questions.
Can I ask another question?
Yeah.
Maybe I missed this, but let's say, imagine you have non-interacting picture and you try to calculate the critical exponent for this dB, right? So it's just a basic question. So there is this nu and z, right? And the nu for the non-interacting case becomes some trivial value. Is it 1? Is it, what is it?
Okay. So I am going to talk about that in just a minute. So good.
Okay, sure. Okay.
Segue question. Yeah. So the value of nu is going to be very central to this talk. All right. So if there are no other clarifying questions, I'll take that as a segue into models. So the most common model for the integer quantum Hall transition was proposed by Chalker and Coddington. This is known as the CC model. And we can draw it pictorially like this. So we're going to extend from the semi-classical arguments that I was making before about filling an electronic landscape or filling a disordered landscape of electrons. And we're going to draw this as a picture. So we have puddles of electrons, and we're going to cut this disordered landscape at a given energy. And to incorporate quantum mechanics into this approximation, we're going to say that there's a non-zero probability that electrons within one localized region can tunnel to another region. So we have R and T, or our reflection and transmission coefficients. And because of the conservation of probability, these are not independent of each other, and we can cast them in a kind of nice way with a parameter that I'll call x today, which is basically the distance energy-wise from the transition. So if we want to see how a quantum Hall transition can play into this model, I think it's instructive to take some limiting cases. So let's take x to minus infinity in this model. So this means that the reflection is going to go to 0, and each node here will be fully transmitting. So in that case, we only allow right turns. So an incoming link scatters to the right here, and then so on. And if we do this for every node in this picture, we'll see that we have in the middle or the bulk of the sample these isolated electronic petals. And the left side of the sample and the right side of the sample don't communicate with each other at all. So this can be thought of as just a normal insulator. Now, if we take the opposite limit, x going to positive infinity, we see something interesting happen, which is that everything pairs the opposite way. And within the interior or the bulk of our sample, we still have an insulator. But on the edges, we have these counter-propagating edge states, which are a good model for the unit conductance that we see in the integer quantum Hall transition. So we can draw a phase diagram as follows. So C here I'm using to label the number of edge states in our system. And from the limits and the symmetry across the limits, we can deduce that the phase transition between these two numbers of edge states will occur exactly at x equals to 0. And we can measure the critical exponent across this transition using numerical methods. And the current consensus in the numerics is that this is about 2.6. So another model that is lesser studied, but also very interesting, stems from this idea of universality classes. So we learned from Duncan Haldane in the 1980s that you don't actually need an external magnetic field to have a quantum Hall effect. And it's possible to, in a two-dimensional sample, engineer the microscopic details of your model to have basically an internal magnetic field. And this is known as a Chern insulator. And it can be described by a Dirac Hamiltonian. So using the principle of universality here, Ludwig and collaborators in 1994 conjectured that if we disorder this Dirac fermion type model, then it should share the same universal properties with the integer quantum Hall transition. And we were interested in testing this numerically. So a little bit of review on Dirac fermions. We described the clean or the non-disordered model with this Hamiltonian here, where the sigmas represent the Pauli matrices, and then this M is known as the mass term. And if we assume translational invariance in both directions, then the momentum quantum number is well defined, and we have energies that split into two bands. So we can see that if we're looking at 0 energy, then the two bands will touch at exactly M equals to 0. And by looking at this relation here, we can deduce a phase diagram for whether or not the system is a metal or an insulator. Basically, does it have a band gap or not? And we see that we have this cone of metallic states that is centered around mass equals to 0 and becomes larger as we increase the energy. And across this transition, we see a jump of 1 in the number of edge states that we can have. So then the interesting question is, what happens to this phase diagram when we add disorder? So let's do a simple addition of disorder. So we can add these disorder potentials, which are varied in space. And then in order to make contact with this theory, we have to add some texture of Pauli matrices. And we learned from Phil Anderson that in two-dimensional systems, we expect all states to localize. And there's a caveat we see in our numerics, and a couple other authors have also seen recently, which is that exactly at this critical point, the states are not actually localized. So we call them critically delocalized. So it's still reasonable to study having a localization length divergence across this transition. And this looks very similar to integer quantum Hall. From this perspective, you have a change in 1 in the number of edge states on either side of the transition. So we did some numerical analysis on this picture. And we basically traced across one of these lines. And we calculated the localization length at each point and saw the speed at which it diverged. And I will also mention that the Dirac model has a nice feature where you can raise or lower this line and see if this critical exponent is stable with raising or lowering the energy as an additional kind of stability check. And the results we found were quite puzzling. So as we raised this line up and down, for higher energies, we found something that was pretty close to the 2.6 consensus for Chalker-Coddington. But if we lowered the energy, and especially at zero energy, we got this 2.33 with reasonably small error bars, suggesting that we were seeing something physically distinct, but we didn't really know what to make of it. And after doing all of these calculations with the conventional method, we were confused, so we used an alternative method. And using the alternative scaling variable, we found the exact same thing. So we didn't really know what this meant. And when we looked at the literature, we also saw some inconsistencies coming up in recent years. So I'll walk you through this brief history. So back in 1988, when Chalker and Coddington originally proposed their effective model, this error bar was very large on the critical exponent. So we knew that the critical exponent was probably 2, but it was a question of 2 point what. And then as numerical techniques got better, first, Huckenstein and Kramer were able to make this error bar much smaller. And then starting in about 2009, Keith Slevin and Tomio Tsuki started considering finite size effects of these models, which they could do as they got model larger and larger systems. And when they took those effects into account, they got a different critical exponent. And then a couple of other authors found slightly in that neighborhood for lattice models. And then another notable study from Ilya Gruzberg and some other people who might be here today was when introducing structural disorder into the Chalker-Coddington networks, they found an incompatible value with normal Chalker-Coddington networks, which was unexpected by universality. And then in the purple study, just added another layer of this looks maybe not quite right. So I want to make an allusion now to last week's talk, where Elaine Spring gave a very nice presentation about amorphous topological insulators and talked about the duck test. Namely, if something looks like a duck and quacks like a duck and walks like a duck, it's probably a duck. So today, we're going to ask the question where we see something that looks like about 2.6, maybe 2.3, and it's about 2, but what if it's not 2 at all? What if there's something completely different going on here?
So, Elizabeth, can I ask a quick question?
Yeah, sure.
So with respect to the finite energy, so yeah, I mean, you breezed through it, but the fact that you find this stack of quantum Hall transitions, again, this is very strange.
Yeah.
In the context of our stuff, Alex Olin and I are trying to figure this out, and we're still stuck analytically. So the question he always asks me is that, how sure are you that this isn't a finite size effect? So let me ask you that. How sure are you that the criticality, particularly at finite energy, is not a finite size effect?
I think I'm going to table that question to the end, if that's okay with you.
Okay, sure.
Yeah, but that is a very good question. So yeah, this mystery of why the critical exponent changes with energy, we will get back to, and I'm happy to stay afterward and discuss a little bit. But for now, I want to present this alternative theory. And to first think about this, I want to dive in and talk about how do we define critical exponents? Where did they come from? And I'm going to explore a new theory that we looked at and how that might help us see that the quantum Hall transition looked like a duck, but is actually something else. So I want to convince you that we can represent this picture on the right, which comes from the experimental data, with the picture on the left, which we call a flow diagram, specifically a renormalization group flow diagram. So these plateaus are going to be represented on the x-axis, And we can see that at integer values of the Hall conductance here, we're going to see these basins. So all of these arrows are flowing into the basins. And then we see these spikes of the longitudinal conductivity. Oh, okay, resistance in the experimental plot. We see these spikes, and these correspond to these positions on the vertical axis. So we're basically plotting these two these two series of data in a different way. And what these arrows are representing is if I'm in a certain state of the system, and then I zoom out, then I will see which state of the system I'm actually in. So if we go back to the puddle picture, we can think of trying to figure out if I'm actually in an isolated region that doesn't look like the whole region by zooming to different length scales. This is called renormalization group flow here. So we would say that if this transition is in an infinitely large system and zero temperature, then the critical point or the transition is guided by a fixed point, which occurs exactly at the midpoint of this transition between the plateaus. So that can be seen here by these black points. So we call these the fixed points, and we say that these fixed points are what drives the transition for the integer quantum Hall effect. So let's think about how to describe this with mathematics. So it's convenient to describe the deviations from the fixed point. I'll call them delta plus and delta minus. So delta plus is going to be what we call the relevant direction. So we see that if we start a little bit off of the fixed point in the delta plus direction, then we flow into one of these basins. So this is relevant because it's not stable. And then the delta minus direction is the opposite. So if we start a little bit further away, then eventually we flow into this fixed point as we zoom out. So it's useful to describe this zooming out as a logarithmic scale, which I'll call L for the remainder of the talk. And then we can describe these deviations and what happens as we zoom out in terms of what we call renormalization group beta functions. So let's qualitatively go through these for a minute. So let's say that I have a positive delta plus. So I start out a little bit away from criticality in that direction. Then this critical exponent nu comes in here, and you may remember that this is a positive number. So this is saying that if I'm a little bit away from the transition, or sorry, a little bit away from the fixed point when I start, then the derivative is going to be positive. So I'm going to grow further and further away, and then eventually fall into one of these basins. Now, the opposite case is true for the delta minus direction, longitudinal deviations.
Excuse me.
Yeah.
Can I have a question?
Yeah.
What is new here? It's a localization less index?
Yeah, so thank you for clarifying. So this nu is the same nu that I've been talking about the whole time. This is the local.
How it's appearing there like that?
So a assumption behind these beta functions is that the linear expansion of whatever function of delta plus and delta minus is that it admits a linear term. So this is just the linear coefficient of the expansion of the beta function.
No, have you calculated it, or it's just an assumption?
Oh, so I'm assuming that it exists and talking qualitatively about what it is right now. But it was what I was showing had been calculated previously.
Have not calculated, or? Okay, thank you.
Okay, so I'm using this as a number greater than 0 here, which can be calculated, but at this point, I'm not going to talk about calculating it.
if it's calculated in what kind of model? I mean, it should be calculated probably analytically.
Okay, so I will talk about an analytic calculation. Yeah, so I will talk about an analytic or a proposed analytic calculation of it in a minute. But right now, I'm not claiming that I know how to calculate it. I'm just saying that it is greater than 0.
So Ara, this is not a number that we know. It's just a description of the standard scaling scenario when you assume that there's a linear term.
Yes, my question was, why in the standard scaling scenario, nu is appearing like that there?
What do you mean? You just integrate this equation, set delta plus to 1, and you call this localization length, and you see how it relates to the. I mean, that's what this is. I mean, it's a standard picture. I mean, I don't know what you're asking about. I mean, right? I mean, just do this, integrate this equation and see what happens. You will get that this is the localization.
Sorry, as a chair, I propose we move on and then postpone this discussion for later if there will be more time later.
Okay. Yeah, we can discuss further after the talk. So for now, we're just assuming that this nu is a positive number. And the fact that it's positive reflects in that if we go slightly away from the fixed point, then we fall into one of these basins as we flow. And then the opposite, because of this minus sign, is true with the stability in the vertical direction. So you can convince yourself that if you go a little bit less, or you go a little bit away negatively from the transition, then your derivative will be positive. So then you'll flow eventually back to this fixed point. So the only way to eventually end up on the fixed point is if you are purely in the vertical direction in your initial condition. Okay. So to summarize what I'm going to call the standard paradigm we presented in the last picture. And we had these fixed points, which I will label with a star. And we had integer number of them in the Hall direction. And then the position on the vertical axis was fixed. And from experiments and numerical calculations, we've estimated that this is about 0.6, but we don't have a precise value or prediction. And then these critical exponents, localization length is greater than 0, and then y, what we call the irrelevant exponent, is negative. So Martin Zirnbauer proposed a conformal field theory in 2018, partially motivated by some inconsistencies in quantum Hall studies. And he gives fixed point values, which of course they should agree phenomenologically with what we see in the Hall conductivity. And then for the longitudinal conductivity, he finds something, an analytically exact prediction. And this is a very interesting tool for us because it looks about like what we've seen before. And then for the critical exponents, he has a completely different prediction, namely that localization length exponent is infinity and y is equal to 0. So this stems from the conformal field theory itself and created quite a stir in integer quantum Hall physics because we didn't immediately know how to verify this or why we had been seeing nu as about 2 for so long. So what we did is we thought about, well, if nu and y are not good descriptions, let's expand beyond the linear terms. So we proposed the following ansatz here, and we chose the signs of these B parameters and also the terms in the expansion that we allowed to conserve the topology of the flow diagram I showed earlier. So we wanted to match the flow diagram because that expresses phenomenology that we see in experiments. So you'll notice if you look at these equations, something nice happens if we set delta plus equal to 0. So delta plus equal to 0 means we're exactly along the critical line. So at criticality, we can reduce this to a single equation with a single, what we call universal number, V1. And we can test this numerically. And furthermore, we have multiple models that we can test this numerical prediction on, and we can see if they agree or not. So I need to introduce one more character in this story, because it turns out that the Chalker-Coddington model and the Dirac model both approach this fixed point from the lower direction, but there's another model that we'll see later approaches it from above. So we can actually have a bound on what this value might be. So this is going to be, I'll call it CC2, and it's basically a two-layer Chalker-Coddington model. So we stack two layers on top of each other, and then at each of these nodes in each layer, we'll define an X parameter. So I'll call them XA and XB, one for each layer. And then at the nodes, the scattering will be what we call layer preserving. And then on these links in between the nodes, that will be where these scattering between the layers can mix. So we can draw a phase diagram for this, similar to the one-layer Chalker-Coddington, and it's a little bit more complicated. So we see that we can vary two critical parameters, and then we have these lines which represent the transition between different numbers of exponents. And I'll come back to these dots later. So now that we have Chalker-Coddington two-layer and one-layer and the Dirac model, we can start doing a calculation along this line. And if I solve the equation from before, we can have a prediction for delta minus, or this deviation, as we increase the length size. So to simulate different length scales, or this zooming out, what we do in practice is we have to construct systems of Chalker-Coddington networks or Dirac models of different length scales. So this will be L, and then this will be some aspect ratio times the length scale. And we replace this model dependently. So to actually calculate the longitudinal conductivity, we think of this picture. So we attach leads to the top and bottom, and then we wrap the size into a cylinder. So we repeat this calculation for each of the three models at various length scales. And then we also we average over many disorder configurations. And we come to the following result. So I will spend a few minutes on this figure. First of all, we expected, as we increase the length scale, to see the critical conductivity approaching 2/pi. And we do see this coming from above and below, which is promising. So we ran two sets of data for the Chalker-Coddington one-layer model at criticality, which you see by this X being set 0. And then for two different aspect ratios. And then we also looked a little bit away from criticality. And we saw, as expected, that it looked like we might be approaching the critical point as we zoomed out or increased the length, but then ultimately we went away from it. So this can be seen as falling into one of the basins here. And then in this brown, we have the two-layer model approaching from above. And then finally, the Dirac model also seems to approach this fixed point. And here W is representing just the absolute strength disorder potentially applied. So from this diagram, we can think about what is B1, this parameter, because that's the only free parameter that we have here. So we can calculate that from the data. And we see something fascinating here. So the one-layer model of Chalker-Coddington and the Dirac and the two-layer model all seem to suggest a value of this B1 parameter that's around 40, 45. And furthermore, I think it's best seen for the one-layer model that as we increase the length scale, this seems to be very stable around the value of 45. So the fact that it's stable as we increase the length size and seems to agree for the three models seems to suggest that this B1 might be some sort of indicator of a universal parameter or something like a critical exponent, even though this theory by Zirnbauer says that critical exponents have vanished.
I want to ask a question. Is your range of length sufficient to distinguish square root of log from some power law? Have you checked to see what is sort of your goodness of fit, various kind of indications of how quality is the fit if you attempt a power law scaling versus a log scaling for these system sizes?
Yeah, that is a good question. So at this point, we do not fit to a power law from this data, at least. But it is true that it has been very challenging to distinguish them from each other. And this has been done in the literature. And the result of doing this calculation is that for the other critical exponent y, there have been very, very wildly differing values estimated in the literature before. So that is a good question. And it had been done before, so we are just looking at the alternative right now.
I see, thanks.
Elizabeth, may I also ask a question?
Yes.
So if I focus on the bullets, dark blue and light blue, then I have an impression that the biggest system sizes have a tendency to go downwards, so that I have a slight curvature to the right. Should I ignore that?
So this is a good question, and we have discussed this before. So I will bring attention to the aspect ratio 6 versus aspect ratio 4 here. And I will point out that the curving downwards seems very much more slight for aspect ratio 6. And Zirnbauer's theory is for aspect ratio infinity. So it is a good question. It is something that we haven't come to a certain answer that we can't disprove. But it is a positive sign in our favor, I think, that we increase the aspect ratio closer to infinity, then we see more agreement.
Thank you.
Yeah, that is a good point.
If I may, I want to have a follow-up question. So from this data, should I interpret this data as suggesting that B1 is universal and model independent, or should I look at the error bars and say B1 is a model specific thing, and for the one layer CC, it's this much, and it's roughly 10% larger for the other one, etc.? Should I see these as being error bars so large that all the B's are universal irrespective of model, or should I take B1 to be model specific based on the error bars in this plot?
I see. Yeah, so we are arguing that there is a possibility that B1 is universal and not model specific, but the error bars, especially for the Dirac, are quite large. So there definitely needs to be more work done to back up that claim that B1 might be universal. Yeah, that is a good question. So I want to bring to attention.
Elizabeth?
Mm-hmm.
So if this difference between dark blue and light blue is important for you, then that difference manifests itself essentially only in one data point. Is that correct? So it's
this data point?
In the dark blue one with a large error bars, that is the only one that actually gives us a clear difference. Not even a clear difference, but some difference between dark blue and light blue. Is that the data point that makes you believe that with increasing B, with increasing A, we go closer to a straight line?
Yeah.
Okay.
That is the main.
Okay.
Main support.
Thanks. I see. Thank you.
So I want to draw attention to a part of this figure I haven't discussed yet, which is these triangles. So another verification of Zirnbauer's theory is not just this B1, but also if this critical value of the conductivity at 2/pi is something special or not. So we also used the same data from the previous slide, and we plugged in slightly different values, varying by about 5% of the fixed point critical conductivity. And we found that for all of the, or both of the models considered here, we seem to have more variation with size of this B1. And B1 changed quite a bit, even with small variations of the critical conductivity. So that lends, I think, a further stability argument to this idea that there's something special about 2/pi that we can see in this data. So the final question I think that should be asked here is why, if nu is equal to infinity, and this actual paradigm that Martin-Zirnbauer exists is correct, why have people in the field been able to calculate nu for so long? So we wanted to think about this, and we proposed an idea of something we call an effective localization length exponent. So if we recast our equations a little bit, these are the exact same nonlinear beta functions from before. If we recast them a little bit, we can see that in place of the relevant exponent, we could consider that this number b times some initial averaged value of this delta minus or rescaled irrelevant contribution might look a little bit like a critical exponent. So to test this, we numerically simulated these equations, and we just chose values of a and b based on a couple of trial runs, and plotted different initial conditions of delta minus and delta plus and what happened when we plotted different initial conditions. So we plotted for delta minus two slightly different initial conditions, and those are shown all in the blue curves and the red curves. And this little L here, which you might remember from before, is the log of the length over some reference length scale. So little L being 0 means that you start at the reference scale and then go larger and larger. So if we have different initial conditions for the delta plus here, so we start delta plus being small in all cases because eventually it will grow to order 1, and then after that it will diverge. And we also can't really trust these equations beyond order 1. So we simulate for various conditions, and we take account of the point where delta plus becomes order 1, and we say that that's our approximation for what the localization length is. And we see that for these two sets of additional initial conditions in delta minus that are only slightly different, if we fit a linear curve here, we see quite different values of this effective critical exponent. And one thing you can notice here is that these are not quite linear. So you have some curvature. So this is just an approximation, but it could account for slightly different critical exponents. So we wanted to next test if we could see a variation like this in the effective critical exponent between our models. So we look at these points on the Chalker-Coddington model diagrams. So for the one layer, you recall we had a transition exactly at x equals to 0. And then for the Chalker-Coddington 2 model, we had this line of transition points. So we looked at two different ones at different locations. And we used a alternative method that we had used before for the Dirac case and calculated a scaling variable, and then found the effective critical exponent from these. So for the one layer model, as expected, we reproduced this 2.6. And then for the two layer model, we saw something that was different than 2.6, but also varied as we went along this critical line, which seems very non-universal and strong evidence that this effective critical exponent might be the real theory. And again, this effective critical exponent would stem from differences in the initial conditions at the reference scale with regard to the irrelevant conductivity. So this is our best guess right now for how we've been seeing estimates of a critical exponent, even if Martin Zirnbauer's theory that critical exponents are different and this whole conformal field theory picture applies to the integer quantum Hall. If that is true, this could be why we've seen something different for so long. Okay, so at this point, I'm going to summarize what we have talked about, and then I will open it up for broader questions. So back at the beginning, we started with this question of let's verify a conjecture about disordered Baroque fermions and see if they indeed have the same criticality or critical properties as integer quantum Hall. So we added disorder to the clean system and looked at a phase diagram here where we saw transition between two insulating phases. And we calculated the critical exponent varying the energy and saw this surprising number, 2.3. And then partly motivated by this, we decided to look at what we call a marginal scaling theory. So by marginal scaling, we just mean that nu equals infinity and y equals 0 in this case. And we have to use nonlinear beta functions to understand the transition. So we looked at numerical evidence for that by going along the critical line, testing this equation from our nonlinear ansatz, and then seeing agreement or hopeful agreement between different models and also robustness to varying this critical conductivity parameter. So I think there are a lot of exciting directions to go from here. We still have to make more contact with the analytical theory and figuring out how to reconcile the numerical value of V1, and also continue to ask if this is true by looking at more models and larger length scales and continuing to discuss with other experts. So with that, thank you for your time, and I will open this up for questions.
Thank you. Any questions?
Yeah, I have one, if I may. So firstly, thanks for the talk, and hi. Good to see you. So in the linear beta functions, in the beta differential equations, the linear coefficient is, well, it's postulated to be universal across different systems. And I presume that this comes from some kind of scale invariance or something like that. And is there a similar argument for the coefficients for the higher powers, that they should also be somehow universal from some general arguments, or is this not expected?
Yeah, that's a good question. So my understanding of this is that these expansions are of functions that come from a underlying field theory, which describes the fixed point. And that field theory is determined from the symmetries. So I would expect that this B1 and other higher order coefficients should also be universal. My colleagues know a lot more about the field theory, so if they have something to say, feel free.
Okay, thanks.
I see, I think, another question from Cosma.
Yes, yes. Your Chocker-Coddington model, was it in class A or class D? And if it was in one, have you already started looking at the other one?
Ah, okay, good. Yeah, so our Chocker-Coddington is in class A. Our Dirac model is in class A. Everything is class A. We broke all of the symmetries with our disorder potentials. And we have not looked at class D or class C or any of the other classes.
Thanks.
If I may, I also have a question. I seem to remember reading, I'm a bit rusty, I must admit, I seem to remember reading that the critical conductivity actually is sensitive to things like boundary conditions and how you define the interfaces of the sample. So do you have any thoughts about that? In particular, since the value of 2 pi seems to be important to the consideration. I might also be misremembering. I'm not quite sure about that, but I seem to remember works about non-universal critical conductivity.
So the boundary conditions that we applied are periodic in one direction. Are you talking about if we applied periodic boundaries in both directions?
Yeah, right. I seem to remember, for example, in class C, if you say take extra, if you attach extra edge states at the edges, the results change. Because the critical wave functions are sampling the complete, are going throughout the complete sample, I thought that the boundary conditions may, after all, matter, which was an extra complication. But I don't quite remember whether it should be relevant in your consideration or not.
Yeah, that is an interesting question, and I honestly do not know the full answer to it. But if you have a good resource to read about that, I'd be interested.
All right, thanks. I see, I think, a question from Igor.
Yeah. So hi, thanks for the talk. So this is a continuation of one of the previous questions, and maybe this is a question to Ilya, as you referred to him, concerning field theories. So on Monday we heard a talk by Martin Zirnbauer, and he announced the values of the coefficients in the nonlinear terms in the bit of in energy flow. So did you compare your results with his analytical predictions?
Yes. So yeah, all 3 of us were at that talk too, and I think that was the first time we had heard of any of these predictions by Martin of B1, and our values do not agree. And he suggested a reason for this as having to do with periodic boundary conditions in both directions and a different renormalization flow. And I do not know how to reconcile this. Perhaps Ilya does. But that is a very good question.
I can. It's not a precise statement, just a vague comment. I mean, so the way I think about it is that his theory is a bulk theory, and there's some coupling constants in this theory, right? And then he says what he can do the RG in some way. I mean, specific way. He's doing OP of these perturbations to find out how the bulk couplings will flow under the RG. That's what he does. That gives him some value for B1 that is quite a bit smaller, I mean, almost 40 times smaller than what we see, right? But then he says, okay, what you actually need to do to compare with numerics is to compute the Landauer conductance in a finite system in our geometry, right? And see how that changes away from criticality. And that is a non-trivial question because of the interference effects and everything. The bulk conductance, coefficient in the field theory, that is the coupling constant, is not should not be equal to the conductance in the finite sample. Right? So it's a separate computation. And the only thing that he could do so far is to compute the Landauer conductance exactly at criticality and confirm that it still gives you 2/pi, which is the same as the value of this bulk coupling constant at criticality. Right? But he didn't compute the Landauer conductance away from criticality. That would be necessary to see what this scaling would be. So it's an open question.
But do you see the reason for this discrepancy to be so?
In the meanwhile, Igor, maybe as an aside, so we were very surprised by this finding by Martin that this B1 in his case is 1.2 or something. And one thing we are thinking about right now is to repeat the transport study using the Kubo formula, because this is what he used. So we are checking literature right now. If anybody knows if Kubo has been applied for the CC model, we would be interested in knowing the reference. If not, that's maybe a thing we're trying next. I wouldn't expect a difference, but who knows?
Hello, can I make a suggestion? Can I ask something?
Yeah.
First of all, it was a great talk, and it's a really nice approach, right? I have a question or suggestion. In some sense, you're trying to prove Zirnbauer's theory, right? But in the same way, it should also work to disprove the old one. So my question is, you showed this nice fancy plot where you showed B1 versus length scales or something like that, right?
Mm-hmm. Here,
Right?
I'll bring it back.
Yeah, that would be nice. Last year. Right.
Oh, wait, no.
Right,
That's
good.
Yeah, oh, this one.
Yes, exactly this one. Did you try to plot something similar in sense of the old-fashioned analysis way? In sense of something like you plotted an expected or an effective nu versus length scales? Because I guess it looks not much worse than that.
I see. So you're saying, so the exponent that would be pertinent here would be y.
Well, y or nu.
So we plotted nu later.
Yeah.
With the calculations about criticality, and we found for the two-layer Chalker-Coddington model something quite far away from the previous consensus.
Right, but here the B's are also quite far away, right?
As in, like, the pink from the blue.
Yeah, that's also about what, I don't know, 30 to 45 is 2.6 to 3.5 or something like that. It's more or less the same ratio or not?
I see what you're saying.
So I have not really an opinion about it, but my gut feeling tells me if I plot the same for nu, I get something which looks very, very similar at first glance, at least. And maybe you can see a curvature there, which has disproves the old way in one way or another. I don't know.
Yeah, so it would be a good exercise.
Just a stupid idea.
Plot. Yeah, it would be a good idea to plot the expected value for y as we plotted B1 here, and we could certainly do that. I guess what you're saying about the slight disagreement here, I think this is something where we need to do more work and also get to larger system sizes for the model.
Right.
I think Martin meant
which is not easy to do with current methods.
Yeah, also new, right? Y is maybe a little
I think
bit
Martin
more.
meant new, the relevant exponent.
Okay.
Yes.
And I can comment on this a little bit. So the thing is that if you look at the numerical solution of those differential equations, where you do see the curvature, right? The range of L is a lot bigger than anything available in numerical simulations, okay? So that's one comment. So if you look at the numerical simulation directly using usual scaling, nu, right? Which Elizabeth showed on the next slide or later, right? Then you see you just see a straight line, I mean, almost no, I mean, no curvature essentially, right?
Yeah.
So hopefully, I mean, it's so you see the curvature here, the little l goes from -7 to -2, which is a huge range.
Indeed.
Right. And if you go to the next slide where you see the actual results from the various network models for the new exponent, right?
Right.
Yeah, here you see it's pretty much straight, but the range of L is only 1 decade. So this is not the same range. That's one story. But I think a significant thing is that the values, numerical values for the exponents, are extremely different for these two different models, and even within one model for two different critical points. Why is that? I mean, this is I think this is a smoking gun. I don't know. We expect universality here, but we don't see it clearly. Right?
Okay, thanks.
I think Matt had a question that wasn't answered, right?
Yeah,
About the
not back.
you wanna give an answer, Elizabeth, or?
Yeah. Is he here?
Yeah.
Actually, sorry, I was cut off when Matt was asking the question. So could we ask him to repeat the question first?
Sorry, are you talking about me or someone else?
Yes, you.
Well, which question? The first one?
Well, I don't know. I mean, something happened. You were asking a question, and then the meeting suddenly.
Oh, I think I was just answering something to Igor, but I did have a question just in the numerics. So because in the first instance of the first paper that you guys did with the Dirac, you find criticality not just at 0 energy but at a range of energies. And again, I mean, you go back to Andreas and company's paper. I mean, they make sort of confusing statements, but at one point, for example, they say that, well, if you had vector potential only disorder and you look at finite energy, everything should just localize. So I think, finding that instead you have this stack of critical states is strange. And it's, of course, similar to the stuff that, Bjorn and I and Said and various people have looked at. But the question is always, is this a finite size effect? So how confident are you that when you look at these finite energy states and you go to bigger systems, that you don't, the thing doesn't eventually localize? And there's no good answer, but I mean.
So may I try to say something here? So Matt, sorry, what's wrong with this picture where you have just a Dirac fermion, and the finite energy it's like a Fermi surface, right? And then you start developing, you add all kinds of disorders, and you actually can map it to a sigma model, right? As was shown by the Carlsbad people, right? So what's wrong with that?
Yeah, what's wrong with it is that, so.
Yeah, excuse me, yeah.
Yeah.
This E here, what is it? Is it indeed Fermi energy at field?
Yeah, it is. Yes.
Then it is, according to our paper, is precisely what we are saying, that if you are changing Fermi energy, there is in our model, there is a parameter P, it's changing according to level of Fermi energy. And then index will flow, as you demonstrated here. Your indices for different different field Landau levels, not Landau levels, sorry, Fermi levels, the nu is flowing. You see?
You're referring to this.
Yeah, but all right, there are no, I mean, this is a different system, so it's a Dirac fermion, so I'm not sure.
There are also Dirac fermions. Dirac fermions, 2D Dirac fermions with field Fermi levels in random potential landscape. They define the effective theory for H, about which we are talking in that article. In that article, it's effective theory for H states of field Fermi levels. Okay, just my impression was, maybe I misunderstood what we are doing here, but my impression is indeed it's somehow it's fitting. And then I was thinking, what is the meaning of? Can you show renormalization group equations?
Sorry, Ara, but I think you interrupted Matt. He was saying something.
Okay,
Maybe.
sorry.
Sorry. Well, okay. So I don't want to get into a long thing about the analytical side of this, but suffice to say, we've been trying to derive this, right? And one of the problems is that most of the regularization schemes seem to show an even odd effect. And we're specifically looking at these A3 surfaces that we looked at with Bjorn in this PRX we had last year. And we don't see an even odd effect. So what you would expect is that if you have two Dirac cones and you have a certain type of disorder, this is a surface of a A3 topological phase, that for even winding numbers, everything would localize at finite energy, and for odd, it wouldn't. But we don't see that numerically. And you can also make, so Alex Ulland is now mumbling something about, trying to connect this to 1D, and now he's arguing that everything should localize at finite energy. So I think analytically, there's a problem. But the question I had was just, how confident are we that we're critically delocalized? Forget about nu, just that the states are critically delocalized at finite energy in this particular Dirac study.
Yeah, so I guess the best answer that I can give for you is that we have calculated the Drude conductivity. Bjorn did this. And I think I have a slide somewhere.
Right, where it was trending the right way.
Yeah, so this slide I have about measuring. So W is the disorder strength, and Bjorn went and calculated the Drude conductivity at varying energies. So this is kind of the only evidence I can really give at this point.
Maybe I can add to that answer. Of course, the Drude conductivity that was calculated on short length scales. That doesn't tell us anything about the fate of the system at long length scales. That's what is Matt asked about. Do you, Elizabeth? Do you have the numerical data of the Lyapunov exponent, the scaling plots? Because that would be my answer. So we have repeated
I don't have it here, but I'm happy, Matt, if you want to discuss.
So I can look it up, but
in
what
our
is it
paper.
exactly?
Yeah, in our paper, what we did, we did the standard study of the dimensionless Lyapunov exponent. So quasi 1D systems, very long, and we were very careful not regularizing on a lattice, but working in the continuum model and determining numerically the Lyapunov exponents for Dirac at various energies. And these plots look exactly the same qualitatively at zero energy. And at finite energy, up to energy 0.7 in units of inverse disorder correlation length, which is the only energy scale that we have here. They look exactly the same. The only difference is really the nu that climbs up from 2.3 to 2.5 something. Yeah. Otherwise, those plots with these crossing lines, right? You need an irrelevant exponent, but these crossing lines and they're exactly the same, independent of energy, and they look exactly as in the CC model and in other models that, for example, Martin Puschmann has studied recently.
Okay.
And that's one part of the answer. The other part is a question back to you. How do you, if you don't want a critical line, how do you reconcile going from Chern number +1/2 to -1/2 without a critical line or any critical phase?
Good question.
You need to offer something else.
Alex was the one pushing this, not me. So I don't. We haven't thought about it in the context of tuning, breaking time reversal. We're thinking of it in the context of these A3 surface states and just tuning energy, and is there topological protection away from zero energy? And just analytically, it's still we don't understand what we're doing. But
I think. So I support the comment by Ilya. So I think the fact that there is quantum Hall criticality for Dirac fermions exactly at this point m equals 0, I think it was demonstrated by the derivation of nonlinear sigma model in different ways for finite E where the conductance is sufficiently large, where the derivation is controllable, and you are exactly at theta equal pi.
Right. You're like your 2007 or 2008 paper, right?
And the other paper where it was derived from non-abelian bosonization.
Right, with Koenig. Yep. Yeah. So I have no problem with those derivations, but I think we're just hitting our heads against the wall trying to understand what's going on in our case. For the single direct cone, I agree.
Okay. So sorry. So I was cut. My connection was cut when you met. Were commenting on my question. So maybe may I ask you to repeat your comment?
Well, so I mean, the only statement I was making is just that, so Martin, of course, phrases everything in the most complicated possible way, but his CFT, as far as I can understand, is just exactly the same CFT we would have to describe the surface of an A3 topological phase with winding number 4. Or more precisely, it's the CFT that describes the zero energy state there. So it's a class A3 Wess-Zumino-Witten model at level 4. Okay. And what I don't understand still is why the conductance is 2/pi and not 4/pi, because for that model, the conductance should be 4/pi. And the special thing about these A3 Wess-Zumino models, as you know, is that there's this abelian disorder strength. You can tune that parameter to make the density of states not critical. And if you do that and you go to level 4, you get the multifractal spectrum that matches what has always been seen in quantum Hall numerics if it's truly parabolic. So, it's like a known relatively simple theory. Where I get lost is exactly his arguments about the delta minus and delta plus here, which is exactly what Elizabeth is computing.
Thanks.
Sorry, if I may intervene here, I actually find this discussion fascinating, but perhaps let's focus on the topic of Elizabeth's talk and see if there are any final questions, because perhaps the CFT is a little bit an aside.
Yeah, it's a very interesting topic, and I refer you to Martin's paper. Where is it? If you want to learn more. And also, if you have further discussion questions, feel free to send me and Ilya and Bjorn a correspondence. So this paper outlines his theory.
Any final questions, remarks? Well, in this case, thanks, Elizabeth. A fascinating work, and thanks everyone for coming.
Yeah, thank you for coming.
Yeah.